When I was young and I was into electronics, even way back in junior high, and things like this I did not understand. I knew what resistance was, but why did Radio Shack sell a cable that had resistance? Who on earth would want resistance in a cable? I thought maybe it was 75 ohms per foot. Well, that didn't make sense. Maybe it was 75 ohms per total, and that didn't make sense either. How did that work? What I really didn't understand was, of course, this is the impedance of the cable. Remember this? Note the inductors and capacitors, and they have implications. So besides being a transmission line model, they actually determine the impedance. The ratio of the inductors and the capacitance determines the impedance as ZO, which is the impedance roughly, this is, simplified, the square root of L over C. As the wave travels, the currents are continuously flowing back to the source through capacitance. I'm going to go over that in slides several times. I'm kind of just going to hit this again and again and hoping that you get it. If you get it already, you can skip forward past some of these things. Okay, as I mentioned, the impedance is the ratio of distributed capacitance and inductance, not capacitance, say it right. Now, this slide, this image here is a nice image from Rick Hartley. He gave me permission to use it. It shows the electric fields on a trace, not only from the trace to the ground plane, but also from the trace to other traces, which of course is an issue. If the trace is wider, its capacitance gets greater and its inductance reduces, so the impedance goes down. If the trace is thinner, the reverse is true. This matters because it affects how easily the trace is driven and how it will respond to a signal. Who knows what the target impedance is? Well, of course, that depends on the buffer, but in general, we like to get somewhere between 45 and 70 ohms. 65, a little bit on the lower side is better, but it depends on what you're doing and so forth. Here we see a system with the trace impedance too low. Let's say it's 30 ohms, and a buffer that isn't designed to drive this load. Say the buffer is designed to drive a 100 ohm load, which is pretty unlikely these days, but let's just say it is. The bicycle, which is the buffer, imagine the bicycle has a regular guy, he's pedaling pretty good. He might be able to pull that load through the trace inductance, which is like a bungee cord, but it's going to be tough. He's going to start to pedal, and it's going to stretch that inductance, and eventually that load is going to move. But it may not have time to get all the way to full speed until the guy has to slow down. So it can have a resulting wave, kind of like that wave up there. It starts out slow, it rises real nice, it may or may not get to full voltage before you switch to the next transition.